Start recording and share the screen. Okay, so we're gonna first start with a couple of examples, a couple of problems that might come up with regard to planes, and then we're gonna continue today with quadratic surfaces. So this is, give me a second. I mean, this is the plane section, not sure. Yeah, 12.5. So one of the questions that you might be asked is if someone gives you two planes, so let's say this is one of the planes over here. Okay, here's one of the planes, and here's another one. To find their line of intersection. So as long as these planes aren't parallel, there is some line where they intersect. Let's say here, this is the line. And you might be asked to find this line. So let me redraw this because it doesn't look great. And so let's say again, you have a plane like this. And you have another plane that looks something, let's say like this. Okay, and let's imagine that they intersect at some line over here. So here's their line of intersection. So how do we find this line? Well, it's actually fairly straightforward. If you take a look at the normal vector of the red plane, so let's say this is the normal vector of the red plane right here. And you take a look at the normal vector of the black plane. So let's imagine that this over here is the normal vector of the black plane. Well, in order for this line to be in both planes, it has to be orthogonal to both normal vectors, right? Because that's what it means for a vector to be in a plane. It's that it's orthogonal to the normal vectors of the planes. And every point in this plane must be therefore orthogonal to both normal vectors. And so what you can do is you can take the cross product of both of the vectors of your planes. So, so you take, let's call this N1 and N2. So you take N1 cross N2. And this gives you a vector that's kind of pointing in the direction of your line. And this is your vector V in your line. So the line RT is equal to R0 plus TV. So that would be this V over here. And then all you need is to find a point in the intersection of both planes. So all you would then need is to find one point on this line, and that would be your R0, and you'll be done. So let's do an example. So let's imagine that we have the following two planes. One of them is the plane X plus Y plus Z is equal to 3. And the other one is the plane negative X plus, let's say, negative Z. So the coefficient in front of Y is going to be 0, is equal to -2. So the first thing to do is to look at the normal vectors of both of these planes. So N1 over here is 1, 1, 1. And N2 is -1, 0, -1. And then in order to find V, so V is equal to N1 cross N2, which is equal to the cross product of I, J, K of 1, 1, 1, and negative 1, 0, negative 1. Any questions so far? Okay. So now this is going to be equal to I times, so we're going to have negative 1 times negative 1 minus 0, so negative 1, minus j times, and then we're going to have negative 1 minus, but then minus, so plus, so negative 1 plus 1, which is going to be 0. Yep. And then plus k times 0 minus 1, which is 1. So this normal vector is going to be negative 1, 0, 1. And this is your vector v. Okay, you're going to have 1 times 0, which is 0, and then minus negative 1 times 1. So that's negative 1. Okay, now what is a point on this line? So, or in the intersection of both of these planes. So if we take the point, point 1, 1, 1. So this point is in this equation, right? 1 plus 1 plus 1 is 3. And it's also in this equation, negative 1 minus 1 is equal to negative 2. So 1, 1, 1 is going to be your point R0. And so then R of t becomes, R of t is equal to 1, 1, 1 plus t times negative 1, 0, 1. Okay, let's try it for t equal to 1. So what is R of 1? It's going to be 1, 1, 1 plus negative 1, 0, 1, which is going to be 0, 1, 2. So is that in this point? So yes, it is. 0, 1, 2. 0, 1, 2. 1 plus 2 is 3, so check for that. And negative 2, z, whatever, negative 2 is equal to negative 2, so it's in there. Any questions about this? Okay, so we saw how to find the intersection of lines and planes, how to find the intersection between two planes. Another question that you might be asked is,
question on what you said.
Yeah.
So when you make the R2 equation, like why do you use the 1, 1, 1 and then the negative 1, 0, 1? Like what?
So we're trying to create a line, and this is the formula for the line.
Yeah.
And the R0 is a point on the line. So I'm taking this point to be the point 1, 1, 1.
So could you have used the negative 1, 0, negative 1 as well?
Is it in both?
Or
You mean 0, 1, 2? You need to find a point in both planes.
okay.
So 1, 1, 1 is in both. 1 plus 1 plus 1 is 3. Negative 1 minus 1 is
Okay.
negative 2.
Okay.
So that's how you get R0, and V you get from the cross product of the normal vectors, and then you just put it into the formula for your line and you get your answer.
Okay.
Yes. Okay, so another type of question you might be asked is, if I give you a point and I give you a plane, what is the shortest distance between that, from that point to the plane? Is this okay? Okay. So here's a plane and here's a point. Let's say that this point is the point 1, 1, 1. And the plane is the, let's say, plane x plus z is equal to 1. So this point is not on the plane. Now, in order to find the distance from the plane to this point, the shortest distance, what you can do is you can look for any vector from the plane to the point. So you find any vector v from the plane to the point, and then you find your normal vector to the plane. So let's imagine that this is your normal vector to this plane. Can anyone have an idea of how to use these two vectors to find the distance from the plane to that point? Yes? Yes, you project v onto n, and that gives you a vector, or if you look at the component, it gives you the length starting, starting from this point to this point, right? And if you look at the vector, it'll give you that vector, but we really only need the component. And as long as we can find the component of that yellow line, then we will have our distance. Okay, so our normal vector is the vector 1, 0, 1. And the homework that I'm gonna send either today or tomorrow is gonna mostly focus in these type of questions to see if you can use projections or different ideas that we talked about to solve a somewhat more intricate problems. Okay, so if this is your normal vector and your vector v, so what's our vector v? If I take, let's say, the point 1, 0, 0, I will get a point on this plane, right? So v can be the vector. So let me call this q, and let me call this p. So v can be, or let me write that here, v can be pq, a vector that starts from p over here and goes to q. And that's going to be 1 minus 1, which is 0. And then 1 minus 0, which is 1, and 1 minus 0 again, which is 1 again. Okay, now that we have v and n, we can recall the formula for the projection. So the projection of, in this case, we want v onto n is going to be v dot n over the magnitude of n. And we also had the normal vector, the unit vector in the direction of n. That's the projection. If we're only looking for the component of the projection, so the component of the projection of v onto n is just going to be this coefficient over here. So that's going to be v dot n over the magnitude of v. Over the magnitude of n, sorry. Any questions about this? And this should be your distance, so yeah. So please take a couple of minutes and find this component over here. And also, once you have that component, try to find the point on the plane. Try to find this point over here. So let's call this point R. Once you have the projection, I would say you need to find the entire projection. Try to find what R is. So what's the point on the plane that's the closest to this point Q? Okay. Okay, so let's do this. Let me see something for a second. Okay, so this is going to be the dot product of these two vectors is 1. And then when we divide by the magnitude of n, the magnitude of n is just going to be the square root of 2. So this should be our distance. Now, if we want to find the vector going, if we want to find the point R, what we can do is we can look at the vector that goes from the origin. So let's say this is the origin 0, 0, 0 to this point 1, 1, 1. And that's just going to be the vector 1, 1, 1. And then we subtract the vector that goes from 1, 1, 1 to the plane, which is just going to be either the positive or the negative. So we're going to have to check, but let's imagine it's the negative of the projection, right? Because the vector going from Q to R is going to be this projection, the entire vector projection, right? Any questions? Yes. The vector V, I mean, there isn't, we're not using cross product, but dot product, yeah. Okay, so what is that vector? It's the vector 1, 1, 1 plus, or let's go minus at this point, minus 1/2, and then we need this times V n over the magnitude of n. So we know that the magnitude of n is the square root of 2, so we can get rid of that square root. And so that gets rid of this magnitude. And so then it's 1/2 of n, which is going to give us, it's going to give us 1/2. So let me erase this 1/2, 1/2, 0, and 1/2. And this is going to be 1/2, 1, and 1/2. So does this it doesn't make sense that this over here is the point R. Can anyone? Yeah.
Walk through your process of what you just did again, with like, 1 over 2 and over the magnitude of n.
Yeah, so we are looking for the point R, and it's a point of the plane. We know that the projection vector is the, so let me redraw this. So here is a plane, and here is a point, and this was the point 1, 1, 1. And the plane had the equation x plus z is equal to 1/2, 1. So what we said is, in order to find the shortest distance from this plane to this point, what we need to do is we should find the normal vector to this plane. So that's this vector over here. And we should find any vector going from the plane to this point and take the projection. Now, the projection itself would give us the following vector. It would give us a vector going from this point all the way to this point. That's the projection. And this projection is given in the form, so if this vector is the vector v, so this projection is given in the form n dot v over the magnitude of n times the unit vector in the direction of n, which is n over the magnitude of n. That would give us a vector going from this point to this point. And we said if you only want to find the distance, you just look at this component over here. But the other question we can ask is find R. Find this point, the point on the plane that's the closest to this point over here. So find this point R. And what we realized that you can do is you can take your projection vector, which is this vector, and you can flip it, which just means put a minus. So now it's starting here and it's going in this direction. And you can see it points at R. So how do you find R? You find a vector that goes to this point from the origin. So let's say this is your origin 0, 0, 0. You find the vector that goes from your origin to this point, and that's the vector 1, 1, 1. And then you add to that the projection vector, but the negative of the projection vector, which is the vector that goes from that point directly to R. So that's what we're doing here. We put 1, 1, 1 over here. That's this vector going from here to 1, 1, 1. And then we subtract, because we want to flip the projection vector. So we subtract the component that we found, which was 1 over the square root of 2, times the unit vector in the direction of n. So times EV, n, sorry, En. So what is En? En is n, the vector n, over the magnitude of n. So we know what the magnitude of n is. You just go to n. What is n? 1, 0, 1, right? That's our n, 1, 0, 1. So the magnitude is the square root of 2. So we can put the square root of 2 down here. We can multiply it by this 1 over the square root of 2, and we just get 1/2. So that's how we got 1/2. Let me actually write this here. So this is going to be equal 1/2. So it's going to be equal 1, 1, 1 minus 1/2 times the vector n. Times the vector n. Okay, and what is this? So this is 1, 1, 1 minus, and the vector n is the vector 1, 0, 1. So you put the 1/2 in and you get 1/2, 1/2, 0, 1/2. And now you just look at what this vector is, and you get the vector 1/2, 1, 1/2. Okay, and this is supposed to be the point R. So R is supposed to be this point over here. Now, again, can anyone tell me if it makes sense that this vector is the point R? What would be the easiest way to tell? Yeah, plug it into your plane equation right over here. Well, 1/2 plus 0 plus 1/2 is equal to 1. So it makes sense that this point lies in our plane. And it would also make sense that it's the point R. Another way of doing this would be, and we can check if we get the same result. So again, here's your plane, x plus z is equal to 1. And here's some point that's away from the plane, and it's the point 1, 1, 1. So what we can say is, well, let's look at the distance formula from this point to all other points. What would that be? So that would be some equation, let's call it some equation f with respect to x and z, or let's go x, y, and z, x, y, and z, which is the square root of 1 minus x squared plus 1 minus y squared plus 1 minus z squared. So for any point now in R3, let's say this point, x, y, z, we have an equation to find the distance between your point 1, 1, 1 and your point x, y, z. It's this equation right over here, right? You just plug in your x, your y, and your z. That will find you the vector going from one to the other. And then, like we know, you use Pythagorean theorem, right? So does this make sense that this equation should be a general equation to find the distance from your point 1, 1, 1 to any other point in R3? Okay. So now, if we are in the plane, so if we're any point in the plane, sorry, there's some step that we have not spoken about in order to do it this way. We will get to this strategy later, but for now, this is the best strategy that we have in order to find the distance between a point and a plane. So does this make sense? Does everyone understand? Yes? Yes. So in this case, here's your plane, x plus z is equal to 1. And here's the point 1, 1, 1. So we just need a vector from the plane to this point, and we'll call this vector v. Now, what is a vector that starts from this point and goes to that point? So let's choose a point in your plane. Let's say that this point is the point 1, 0, 0, because that works. If you plug in 1, 0, 0 in your equation, you get 1. So that works. Now, was that, by the way, what we used? Let me just v. Yeah, 1, 0, 0. Okay, now then for v we got, so v at this point is going to be the point going from P to Q. So this is the point Q and this is the point P. So that's going to be 1 minus 1, which is 0, and then 1 and 1. So that's going to be the point V. Now we look at our normal vector. This is our normal vector n. And what's the normal vector? It's the vector 1, 0, 1. Okay, and now let's say we just want to know the distance. So we can find the component of the projection. So we know that the component of the projection of v onto n. So that's the projection of the vector v onto the vector n, which gives you this length over here, from here to here. And that should give you your distance from the plane, the shortest distance from the plane to this point over here. And so you need to remember the formula for projections, or at least the formula in this case for the component of projections, and that formula is v dot n over the magnitude of n. Now v dot n, so that's going to be this n, and then dotted with v, which is equal to 0, 1, 1. So that's going to be 1 over the magnitude of n, which is the square root of 2. So that's the shortest distance from the plane to that point, which actually makes sense for the following reason. What's the point R? What was the point R that we found? The point R was the point 1, 1/2, 1, 1/2. So let's do that here. So we have this point 1, 1, 1 and 1/2. Okay, 1, 1, 1. And another point. So this is the point Q. And another point, which is the point 1/2, 1, 1/2. Let's find the distance between these points. So the distance between P and Q is the square root so let's go, oh, sorry, P and R and Q. Okay, R and Q. So let's take the point Q and subtract from it the point R. So 1 minus 1/2 is 1/2 squared. 1 minus 1 is 0. 1 minus 1/2 again is 1/2 squared. Okay, so this is going to be equal to the square root of, okay, we're going to have 1/4 plus 1/4, which is going to be 2/4, which is 1/2. So the square root of 1/2, which is equal to 1 over the square root of 2. So that's the distance, and that's what we found earlier. We found that the distance is 1 over the square root of 2. Does this make sense? Any other questions? Yes.
Did you find the normal vector or you give it?
You find it by looking at the plane.
The normal vector is the coefficient of the plane.
Yes, yeah. For A, B, and C. So if you have your plane is AX plus BY plus CZ is equal to D, the normal vector is ABC. Any other questions? So already in planes, we saw a couple of uses for the cross product, right? We use the cross product either to find the plane itself, if you have 2 points in your plane. So here's your plane, and you have 3 points in it. Then you find the vectors between these points. So let's say the vector going from there to there. So this is, let's say, N1, not N1. Let's call it V1. Nope. V1 and V2. And in order to find your normal vector, we look at V1 cross V2, and this is your normal vector. So that's a use for the cross product. We also saw, with regard to planes, We also saw that you can use the cross product to find the line of intersection between two planes, which was over here. And we also saw that you can use the dot product with projections to find the distance between a point and a plane. So all these tools, cross products and dot products, are already being introduced. And I again would recommend that you remember the ideas, the intuitions behind this. That way, when you're asked a question, even if it's not exactly what you've seen before, you can try to think about, oh, how do I use the normal vector? How do I use the dot product in order to solve these type of questions? Okay, so we're going to stop here.